I want to take a step back today, and I want to go back to section 10.5. We're leaving chapter 13 for today, and I want to talk about something called a parametrized surface. And so by the end of the day, we should be able to define a parametrized surface, match a parametrized surface to its equation, and find parametrization for some common surfaces. All right. Now, let's begin with just a discussion. We have these objects called curves, right? And it was essentially a one-dimensional object that lived within two-dimensional or three-dimensional space, like a wire or a string, or mathematically, we might include a circle, the not including the interior, but the boundary of a circle, the boundary of a disk, or any kind of graph. These are all examples of curves. And when you were in Calculus 3, you introduced the idea of a parametrization for a curve, which for this one-dimensional object took in one variable, and in order to put it in two- or three-dimensional space, the parameterization output a two- or three-dimensional vector corresponding to a position in three-dimensional space where this curve lived. And so as t varied, we had this function r, and the vector r of t pointed to different locations on the curve. For example, t equals 0 might point here, and t equals 1 might point here, and so on all the way down the curve, as an example. Now, a curve is essentially a two-dimensional object occupying 3D space. In real life, when you think of a surface, you might think of, for example, a bed sheet, or maybe a sheet of aluminum foil or a piece of paper, something that's very flat but maybe has been bent or crumpled or curved a little bit and occupies 3 dimensions. Mathematical examples, we have spheres, not including the interior but just the outer shell of a sphere, the boundary of a cube, or the graph of any two-variable function, such as the paraboloid or the cone that we have seen. And so let's introduce the idea of a parametrization for a surface. It's a function which takes in two variables corresponding to the 2D nature of the surface, and it produces a three-dimensional vector corresponding to the fact that the surface lives in three-dimensional space. And the parameterization is still usually called r, but r is a function of two variables, u and v, and produces three functions x, y, and z. And as u and v vary, the vector r of uv points to different locations on the surface. So as a traditional example, you might see a sheet that looks something like this. Different u's and v's inputted into this function might point to different locations here. It might point up to this location if u is 6 and v is 1, or it might point over to this location if u is 6 and v is 2, or it might point over one grid line up if, for example, u is equal to, let's say, 5 and v is equal to 1. Different values of u and v will create different locations on this surface. So let's, as an example, describe the surface with the following parametrization. X of uv equals 2 plus cosine v, quantity times cosine u. Y of uv equals 2 plus cosine v, quantity times sine of u. And z of uv equals sine of v. Now, this is a very famous surface, actually, and what's going on with these parametrizations is indicated over here in this following example. So, we begin by moving some direction in the xy plane, determined by the angle u. So, we travel along the angle u, And here we have cosine u, which is telling us the x-coordinate that comes from moving through an angle u. And here we have the y-coordinate, which comes from moving through an angle u. Now you travel along that angle u until you reach this point, and then you stop, and then you allow yourself to move in a different direction along a second path, which is determined by this angle v. You allow yourself to move in a circle determined by this angle v. So you pick a direction in this angle v, and you travel out for a while, and then you end up in this location indicated on this cyan circle, where u and v both are allowed to go from 0 to 2 pi. So let's imagine this. We have some xyz plane. We have some circle on which we can do our initial travel. And then once we reach that point, we can travel along any circle. Reachable from the initial circle. This is a little bit hard to visualize, but maybe you can see it. Circles around this central circle. I'm stalling so I can give you time to think. The surface that's being described here is called a torus. In colloquial terms, we might think of it as a donut. You can sort of see the central circle running through the center of the donut, and then the circles perpendicular to the first one come around and form these bands around the outside of the torus. So this is a parametrization of a donut called a torus. There are a few more famous shapes, which you'll get to see in your homework and exercises. But let's deal with one quintessential parametrization for the surface formed by graphing a function f of xy. So we want a parametrization for the graph of a function f of xy. Now, do you remember that a parametrization for the curve formed by graphing y equals f of x, there was a quintessential parametrization for that curve, which was to take a parameter t and let t itself represent the x-coordinate, and then plug t into the function f to represent the y-coordinate. So x of t was equal to t, and y of t was equal to f of t. This was in Calculus 3 that we determined sort of a canonical, clear, easy, cheap parametrization for the graph of a function of one variable. We're going to do something similarly cheap to parameterize this surface of two variables. And so we're going to establish the two parameters, u and v, and we're simply going to let x be represented by u, we're simply going to let y be represented by v, and finally the z-coordinate will be determined by plugging u and v in for x and y into the function. So for example, the graph of f of xy equals x squared minus y squared can be parametrized rather cheaply by the choice that x will be represented by the parameter u, y will be represented by the parameter v, and then the z-coordinate will come directly from the output of the function, not x squared but u squared, not y squared but v squared. This is a very typical go-to parametrization for the surface obtained by graphing a function. So here are a few quick examples to solidify the idea, and you'll encounter many, many more. Now, time from time, you may find it easier to use technology to graph a parameterized surface. So let me show you some resources that you can do to graph surfaces, parametric surfaces, technologically. So here I am on GeoGebra with their parametric surface grapher. And to get here, the truth is that all that I did was I googled graph parametric surfaces, and GeoGebra came up as the number 3 option, and I clicked it and it brought me here. So it gives you the opportunity to type in the functions that you have for x of u and v, y of u and v, and z of u and v. And here's from our Torus example, and as you can see, GeoGebra has just gone right ahead and graphed our donut for us. Now, there are some pretty neat sliders here at the bottom which tell you what sort of points different values of u and v are pointing toward. So for example, as you vary u, different values of u are telling you different values along which you're getting these bands here. And then different values of v are telling you how far up and down that circle you end up traveling. And then where the yellow circle and the blue circle meet, this is the point on the torus that is being pointed to by your parametrization. So this is another website where it's fun just to sort of go in and toy and play. For example, we can also enter in our parametrization uv and u squared minus v squared. And it's sort of off screen here. I do have a little bit of trouble with GeoGebra getting their axes to cooperate with me, but sort of off screen you can see a graph of the surface that is being determined by this function f of xy that we saw in the notes. So feel free to go out and play. If you find a better website, feel free to let me know. There may be one that you prefer to this, so just let me know if you have one that you prefer to GeoGebra's website.